Introduction to the choice modeling. Revenue management models were originally developed under the assumption of a stochastic independent demands. But this is not justified because the demand for the particular product may depend on the set of the competing products that were supposed to be available in the market. For example, when the product is removed from the assortment, there will be three scenarios. Its demand may be recaptured by number one, the another product in the assortment, or it may spill to the competitors. Third condition will be the no purchase alternative. Conversely, adding a product to the assortment will have two types of effect in the market. Number one, the cannibalized demand for the other products in the assortment, or number two, may induce the new demand.
Hello everyone, welcome to Kepler. I am your host Gajanan Lokande. This is first video of continuous series of total revenue management, which will cover some models of the choice modeling. This series is divided into the 5 sections. Section 1 covers choice modeling, section 2 will cover assortment optimization, section 3 will cover dynamic pricing, section 4 will cover single resource revenue management with dependent demands, and section 5 will cover network revenue management with dependent demands. Choice modeling are of 11 types, which includes discrete choice models, maximum utility models, random utility models, basic attraction model, multinomial model, Logit model, generalized attraction model, nested Logit model, exponomial model, random consideration set model, bounds and approximate choice models, and Markov chain models. Choice modeling includes these 11 types of choice models, among which discrete choice models, maximum utility models, random utility models, basic attraction model, and the multinomial Logit model will be covered in this video. The remaining 6 models will be covered in upcoming videos. Kepler is the operation research software that provides solutions to the industries for the supply chain optimizations, among which one of the product is Total Revenue Management Solutions. So log on to www.kepler.in and get your complete Total Revenue Management Solutions.
In this video, we study the discrete choice models that help to capture demand as a function of offered products. Means we consider that the demand will change if we introduce, modify, or remove the product. Consequently, when discussing discrete choice models, we pay particular attention to those discrete choice models that are rich enough to capture the substitution effect, and for which the corresponding optimization problems are computationally tractable. Discrete choice models. We will assume that the set of the potential products that could be offered is given by the set N, which contains the products 1, 2, 3, 4 up to N. Here are some values that we will require to optimization process. First one will be the probability of the consumer selecting the jet product, which is denoted by P of S. Second one will be the probability of the sale when the subset S is offered of the jet product, which is given by the PS of S. Here the first one is selecting the product and second one is selecting the sale taken place. Third one will be the probability of the consumer selects an outside alternative is denoted by P0 of S. The probability that the consumer selects an outside alternative is denoted by P0 of S, which is equals to 1 minus the probability of the sale multiplied by demand. An outside alternative may mean either that the consumer does not purchase or that he purchases from another vendor. Fourth one will be the price of the jet product, which is denoted by SPJ. Fifth one will be the cost of the jet product, which is given by CPJ. The vectors for the price are given as SP1, SP2, SP3 up to SPN, which is selling price of the first product, second product, up to selling price of nth product respectively. Same goes with the cost of the product, which is denoted by CP and given by CP1, CP2 up to CPN, where the CP1 is cost price of the first product, CP2 will be the cost price of the second product, and CPN will be the cost price of the end product. Then the expected profit obtained by offering the subset S is given by R as a function of set S and the cost of the product, which is equals to selling price of the jet product minus cost price of the jet product multiplied by set S. Then the expected profit obtained from offering the subset S is given by revenue, which is function of the set S and the cost CP, which is equals to price of the jet product minus cost of the jet product multiplied by probability of selecting the jet product, which is given by Pj of S. The assortment optimization problem is that of the finding subset S, which is subset of the set N, that maximizes the revenue as a function of the set S and the cost of the product, which is given by this formula. Here we need to maximize the revenue with this formula. The assortment optimization problem is combinatorial in nature and arises frequently in retailing and the revenue management. If the prices are also decision variable, then the choice models need to be price aware. Let Pi, which is function of the set N and the cost price Cp, be the probability of the selecting the product I when the set N is offered. We are interested in maximizing the revenue as a function of the price and the cost of the price, which is given by price of the jet product minus cost price of the jet product multiplied by the probability of selecting the jet product, which is function of the set N and the price P. For all vectors, price is greater or equal to the cost price. For many choice models, if Pj is equals to infinity, then obviously the probability of the selecting jet product becomes 0, indicating that the optimizing over the prices could implicitly select an assortment products to offer. Notice that under the discrete choice models, a consumer will select exactly one product from the set S plus when the assortment set S is offered. This is appropriate for the transportation and lodging choices. Later we describe the models that relax these assumptions that may be more appropriate in retail settings where the consumer may buy more than one product. Maximum utility models. Suppose there is a full preference ordering among the products by the consumers. We assume without loss of the generality that the products are labeled so the preferences are first product, second product, up to nth product. Consumer have given preferences here. Here the assumption is that the rational consumer will buy the product which have maximum utility product. But if he considers budget, he will compromise some features and utility and will move up to the second less product. If not that, then the third less utility valued product. Maximum utility model assigns Pi of set S, which is equals to the 1 for the set I belonging to the set S. If and only if J is belonging to the set S, where J is equals to the I and implies that the J is less than I. In other words, the consumer selects an highest rank product in the set S, which corresponds to the product with the highest utility in the set S. The maximum utility model is often presented by assigning a cardinal utility. The maximum utility model is often presented by assigning a cardinal utility, say, and it is denoted by UI, where the I is belonging to the set N. If UIs are all the different, then we can order them U1, U2, U3 up to UN. And for any set S, which is subset of the set N, the maximum utility UI is attained by the highest rank product in the set S. U1 which is less than or equal to U2, which is less than or equal to U3, which is less than or equal to up to UN. Then there may be more than one product in set S attaining the maximum UI, in which case the choice probabilities are assigned uniformly among the such products.
All the random utility models satisfy the regularity property that the probability of choosing a product does not increase as the products are added in the assortment. There are known cases where the regularity property does not hold, and you should be cautioned that in such cases there is a cost of the approximating the choice models by the random utility model.
Is a discrete choice model where each product J belonging to the set N has an attraction value Vj which is greater than 0, capturing the attractiveness of the product J to a consumer. Similarly, the attraction value V0 which is greater than 0 represents the attractiveness of the no purchase alternative. The choice model is given by this formula, where Pj of S equals to Vj upon V0 plus capital V of set S, such that J belongs to set S, where capital V of S is equals to J belonging to set S, Vj. Consequently, the products with the higher attraction values are more likely to be selected. Introduction of the basic attraction model is based on the postulating two choice axioms and demonstrating that the discrete choice model satisfies the axioms. Discrete choice model satisfies the axiom if and only if it is the basic attraction model form. To describe these axioms, we need additional notation. For any subset S which is subset of set T, let Ps of T which is equals to the summation of Pj of T denotes the probability of the consumer selects some product in set S when the set T is offered. Also, Ps plus of T is equals to Ps of T plus P0 of T, which is equals to 1 minus P of T slash S of T, where the T slash S is the set difference of the T from the set S. Multinomial logic model. The celebrated multinomial logic model is a special case of the basic attraction model that arises from the random utility model. Under a random utility model, each product J has a random utility capital Uj which is equal to the Uj plus small e for J belonging to the set N plus, and the probability that the product J belonging to the set S is selected and given by Pj of S, which is equal to the probability of Uj being greater or equal to Ui such that I is belonging to the set S plus. We can think of the Ej as an idiosyncratic variation. On the mean utility or as errors in the measuring utility. If the Ej is a normal random variable, then the resulting choice model is known as the probit model. Unfortunately, there is no closed form expression for the selection of the probability under the probit model, and that has discouraged its use to the certain extent. However, the closed form of the expression for the selection probability can be obtained if J belonging to set N plus are modeled as the independent and identically distributed Gumbel random variables, all having the same scale parameter. The cumulative distribution function of the Gumbel random variable x with the location v and the scale parameter psi is given by this formula. The mode of the distribution is given by v, while the median is given by v minus natural log of 2 divided by psi. The mean is given by and denoted by capital E of x, which is equal to the v plus gamma divided by psi, where the gamma is Euler's constant. Variance is given by the variance x, which is equal to the pi square divided by 6 by psi square. To obtain a mean zero random variable, we state v equals to the minus gamma divided by psi. Notice that the variance is inversely proportional to the psi square. If with the scale parameter j belongs to set N plus are the mean zero Gumbel random variables, all psi and independent across the products, then Pj of S is given by this formula. There is condition, the j should be belonging to the set S, and this is known as the multinomial logic model. And a special case of the basic attraction model, as the psi becomes large and the variance of the j becomes small, and the choice probabilities concentrate on the product or the products with the largest mean utility. Thus, only the products with the largest mean utilities are purchased, resulting in the maximum utility model. On the other hand, when the psi becomes small and the probability of the selecting any offered product converges to the uniform distribution, where each product is equally likely to be selected, this behavior arises because when the variance is much larger than the mean, the consumer loses its ability to reliability.
Coming to the conclusion, today we covered about the choice modeling types and their application. Kepler is the software that provides complete revenue optimization solution just like the choice modeling and many more. To know more about Kepler, please log on to www.kepler.in. If you like the video, please hit the like button, subscribe the channel and push the notification bell. And do follow us on LinkedIn, Instagram, Facebook, Twitter to get more related revenue optimization solutions. Thank you.